All right, so my name is Todd Montgomery. I've been around doing network protocols and around the geekier parts of protocol design and the standards bodies for probably way too long. And I've been around messaging, especially in the capital markets, so trading, exchanges, things like that for basically the last 15 years, maybe slightly longer. So I come at this looking at it as this is actually one of my favorite topics, right? Message passing and protocols is actually something that I've had a passion about for a very long time. And so I'll start off by saying that actually life is event-driven. It's basically message-driven. In fact, you know, these are an example. We have a few other examples too. I'm sure you guys are all familiar with, voicemail and email, right? And so, you know, it kind of looks a little bit like this, right? At times. You know, we kind of get inundated with messages, and they come in all kinds of different flavors and everything else. So to us, I often use the analogies of like mail, postal mail. So you'll see that, scattered out through this presentation as well. But actually, our CPUs that we use are incredibly message-driven. Here's one example. This is a slide from Martin that basically shows the different memory hierarchies within a CPU. And how they communicate with one another is actually over a bus. It is actually over something which passes messages back and forth and gives the illusion of consistency. So it even goes even deeper than this. So I don't expect you to really see all the text up there, but this actually shows how the Haswell execution engine actually has instructions, and they kind of get queued and they kind of get passed around. So even at the lowest level, the opcode level, we actually have message passing systems in everything that we use in computing. This, how many people have seen this before? Probably a few. This is actually the cache coherency protocol that's used between the different caches. And it has, in this version, has 4 states. And in the different ways that the messages that are used to basically make those individual cells move from different states from one another. So it's very deeply ingrained in us, in the CPU, the idea of a network on the CPU and sending messages around. And we actually have one other thing that's very heavily message-driven. Browsers. How many of you are JavaScript developers? Good, I'm not going to offend anyone. Because, you know, web developers actually, a lot of them that I've met recently, they understand the idea of message-driven systems really, really well. Because you're dealing with, you know, a GUI or you're dealing with something else, the idea of passing messages around and having all that is kind of ingrained in that. In fact, things like workers and other things which are kind of, quote unquote new in that space, they kind of have that ability in them. They kind of have these things kind of built into them. Why is this? You know, why do we have all these systems which kind of share this message-driven approach? That's a really interesting question. And as I sort of thought about that, the most scalable, resilient, and fast systems that I've seen kind of share a common set of principles. They kind of break things down into this elastic, responsive, and resilient way with message-driven kind of facilitating these other traits. And that actually is how the Reactive Manifesto is kind of structured, is message-driven is one of the approaches that is usually used to get these traits. It's by no means the only one, but it is a very common one. But why message-driven? What is it about message-driven types of approaches that they seem to allow these systems to be built, at least with our understanding? And as I thought about this, it's really not what message passing provides. It's actually what it makes harder or even impossible. So if you think about it, boundaries are really, really important. Boundaries give you the idea that you want to actually have something which is very tightly controlled, or in some cases, you know, something that you can basically make sure that you feel comfortable with. And so having boundaries that you kind of constrain a design to, and components of the design, and assign priority, and also these the way that you do something, is actually kind of important. How many of you have seen this book? And this is a book that actually talks about how if you put a system under stress, it kind of, and you kind of refine it, it actually kind of develops an anti-fragile mindset to it. But actually, I think this also talks a little bit about boundaries, because as you put boundaries in place, that's one way to make a system less fragile. And these boundaries help quite a bit. What they really do is they give you this forced decoupling and the separation of concerns. And if we even look at this a little bit further, right, these are the different properties that you can kind of see. A binary boundary, where it's impossible to like ship a whole database across the network, because that would just be stupid to go ahead, shift the database over, add something to it, and shift it back, right? An asynchronous boundary, where things that have to be done sort of synchronously have to be broken apart. They present you with this nice ability where you have to break that. You can't do that. You don't have the luxury of it. Or if you do, it has a penalty associated with it. Ordering is something that is actually something that I looked at really closely for several years when I started in my engineering career. And ordering is one of the things that we'll talk about a good bit here, because ordering is an illusion. And it's an illusion at a lot of different levels. And sometimes you need ordering, sometimes you don't. And the other part, errors is messages. A lot of times, if you want to fail something fast, the best way to do it is simply, go ahead, send a message, and then fail. That actually is the idea behind a lot of different systems where you fail them very quickly, you try to do something locally, and then you just ship off an error and then fail fast and let something else that can maybe have more context take over, or just try it again. That kind of concept is, we'll show one or two examples of that. So I kind of postulate that message-driven systems by nature have this asynchronous binary boundary that they've been placed in them. And by having that in place, the designs of these systems tend to locate around different designs that facilitate these things. So let's talk about asynchronous first. So, let's bash on HTTP a little bit. Request and response. You send a request, there's some processing that's done, a response is generated on the other side. And if you're not in a browser, you may be doing this and you may be actually waiting for that response. You could do stuff while you're waiting, and you probably should, because if you don't, it looks a little bit like this. You're at the mailbox waiting, for the response to your letter, which seems just absolutely nuts, right? Waiting at the mailbox, unless you're going to actually find a cat in it like that, probably is, kind of boring. So you'd like to be able to take advantage of other resources while that is being processed. And we all know this. We kind of look at it, and a lot of times we look at it and we say it may be hard. I want to show you something about how you can even take something which is normally coupled really tightly and decouple it just by taking it apart. So let's think about this. What we'd like is there on the right, asynchronous requests and responses. And what we have is a series of requests. Now, these are not these are not synchronous. You're sending a set of requests, you're getting responses back. This is done deliberately to show you this is what you want. Now, how would you actually control this? Because if you look at it, it's actually just simple chaos, right? How do you know which of those responses go with which request? Well, the answer is you don't. And that's actually the secret. It's all about correlation. Simply assign, an ID to each of them and have it echoed back. Not many of you are web developers. That's a cookie, right? You can do that with a cookie. You can do that with all kinds of different things. It's all about correlation. Once you have this, you can do a couple other things. You can get rid of the actual interactions because they actually don't matter. What matters is the ordering. And it's the relationship between those different requests and responses that actually is what matters. In fact, I can change this up and it's still valid. I can reorder them. But I have to reorder them with a request comes before its corresponding response, right? That's it. There's nothing more complicated than that. We can also handle the unexpected with this really, really easily. We can send a request for 0 and we get a back response for 1, which we don't know about. What will we do? We just drop it. Now, we could generate an error, send it back, all kinds of different things we could do. But in essence, we can find that really, really quickly. So this whole idea of, it's hard to do synchronous, type of calls, or it's easy to do synchronous calls, and that they give us lots of different things, like they make error handling, easier. That's total hogwash. It's hard to keep track of these things and know when to time state out. That's not that hard. These things have been going on for a long time. It's actually easier doing it this way. Binary. A binary boundary is one that it's really hard to do certain things across. Here's an example. That's a UML chart. No, it's not really UML. It's showing the relationship between certain objects in a system. Think about if you had to actually take that whole thing, then call a method on it, and then pass it around. That would just be insane. Well, there are systems that do this. There are systems that do this, and they do it for a reason sometimes, and sometimes they just do it because, well, that just seemed like it was expedient at the time. But when you have, a binary boundary, you can't conflate and you can't couple these things together. The real problem here isn't that you want to ship all this around. The real problem is that all that is connected together and coupled. Once you have to break it apart, you have to find a way of actually referring to all of that. That's one way. It's just an account ID. There's nothing more complex than that. These are things that we normally do. And we do them for some reason or another, simply because it's easier, or it's how we're going to refer to it in a database or something like that. But in essence, it's the same thing we would have to do if we actually had a binary boundary between the different things we wanted to do. So once we do that, it's harder for us to couple and conflate these different ideas. Ordering. Ordering is one of those things that unless you start really playing around with things at a very low level, either in the CPU or on a network, you may take for granted. And I'll say this, packets that are sent on a network, and I'll even bring it up a notch and say messages. They can be duplicated, okay? A message sent that's in the general internet may be duplicated. Why is it duplicated? It can be duplicated due to routing. It can be duplicated due to multiple lines. It could be duplicated just because it got duplicated by an element that was wrong in the network. The internet is incredibly sloppy. There's all kinds of things that go on. Two messages can get reordered. One can take one path through the internet, another can take another path through the internet. Sometimes routers will accidentally reorder messages. Switches can reorder messages. Lots of different things can happen. Messages obviously can be lost. And due to transmission error and congestion and a host of other things can cause any message sent to be lost. But you may be sitting back and sort of saying, okay, well, yeah, at the lower level, but I don't deal in that. I just use TCP, right? You may be sort of like Yao Ming and just sort of say, well, I just use TCP. That's just funny. But actually, is that really the case? Do we actually have the case where if we were to think about what can happen to a TCP connection and what that infers about the data, TCP connections can be closed unexpectedly. We can be sending something on a TCP connection, it can be closed. What made it to the other side? We don't know. It can end at an unknown state. You can actually have a TCP connection that, as it's sending data, gets cut. You don't know what the other side got. You may not even know what made it out and what is possibly made it to the other side. It can be intercepted by idiots, proxies. So this is more a jab at more the state of HTTP in the general internet today, but there are proxies and there are intermediaries out there that do really weird things. So REST calls can get really odd behaviors. They can get duplicated because of certain proxies. They can get lost due to certain proxies. They can get all kinds of different things that can happen to them. And that's not even before you start talking about things like WebSocket or even things like HTTP2 and other persistent connections where it just totally breaks some proxies altogether and breaks those protocols. So when you start thinking about this, what happens if you combine TCP, right? And you say you want to put data over top of it, and you're going to do things like handle reconnects. Well, guess what? Data can be duplicated. Messages can be reordered. They can be lost. This is a common thing that people do. They end up designing a protocol, and they assume that TCP will always provide them with duplicate-free, non-reordered, non-lost messages. And then they start to do things like do reconnects and things like that, and things break all over the place because it was never designed for that. So when you think about ordering is one of the hardest things to get right, but when you get it right, you don't have to worry about these things because they just fall out. And this is really only when connections are reestablished. When you don't have to worry about reestablishing connections, you don't have to think about things from one connection to another, a lot of these things go away. But that's not always the case. A lot of times in our connected world, this going into a train tunnel and then coming out the other side may lose connection. Now, what about how that message or anything else that was being done between that, how does it function? Like I said earlier, ordering is actually an illusion. None of the things that we have in this world in computing actually guarantee ordering at the lowest level. They all have different aspects to them. And let's take a look at it. Compiler can reorder statements. Runtimes can reorder statements. CPUs can reorder statements. All three of these can reorder statements. Now, does it mean that we have total chaos? No, because we actually have that illusion of ordering that is actually placed on top of it that gives us the feeling that we can think about how different things work. And this is really why, from my perspective, lock-free programming shares the same kind of behaviors with protocols. If you think about protocols, ordering is really, really important for messages, the relationship between them, the interchange of them. And I actually think about lock-free programming as the exact same thing. I think about not at, this piece of memory may change. I think of it as there's a message that's trying to store that value in there, and at some point, someone else is going to be receiving it, and what the order of those events can be. So I think it actually helps, or at least it helps me. I always have to put these things in perspective for, kind of what your background is, right? It goes even more than that. This illusion, which is a good illusion, because if it didn't, we'd just have total chaos and nothing would work, is also in the memory models for, the x86 architecture in Java and C++11. They have memory models which provide sanity on top of all the different things that can happen. Now, the reason why a lot of that reordering happens, efficiency. And a lot of reasons why ordering in networks happen is efficiency. So that's a little bit about how ordering is an illusion. That's a little bit about what we can kind of think about in terms of ordering, and and maybe opening up a little bit more. Let's talk about different types of ordering. One of the speakers that you'll see tomorrow, Leslie Lampert, has done some incredible work earlier in his career on total ordering and different types of ordering and what it means and how systems that have been developed that way have provided it and what the value is of them. When that work came out, I was actually a young grad student working on my master's, eventually my PhD at that time, and it had a very profound kind of impact on how I viewed that stuff. So I'm really looking forward to his talk tomorrow, but I know he's not talking about that, but I have questions. Source ordering. This is your basic ordering that you normally think about. Message A and B from the same source are always ordered. So if message A is sent and message B is sent, message B arrives after message A, if it's from the same source. From different sources, they get ordered different ways. Total ordering. Back in the early 90s, total ordering systems were actually very common. There were several of them around. Some were research, but there were also some that were used in terms of like the New York Stock Exchange and several other exchanges as well as trading houses. Total ordering basically says that if message A and B from any two or more sources are ordered the same at all destinations. What that means is that if you have multiple receivers, you can guarantee that message A and B will always appear message A then B at all destinations. That's total ordering. It's an illusion, just like the rest of ordering. It's basically bordering on delusion, because by doing that, you make a very serialized system that has certain kinds of requirements within it. Providing that locks systems in pretty hard. In fact, it almost provides arbitrary latency penalties that are attached to it. But there are certain things that become much simpler when you can assume total ordering. When you can assume total ordering, you can also assume that all receivers and all destinations see the data, that stream of data in the same sequence ordered between sources. I like something called causal ordering. So total ordering is really painful. It really makes things really difficult. Providing it's not that hard, it's really what the systems then, the impact of the systems really is. Causal ordering is different. Causal ordering says that I don't care about the ordering if these things aren't related. So you can think about it from an exchange point of view. A trade that happens on one instrument doesn't have to be ordered with the trades for another instrument. Technically, there are other options where it might need to be. But if B causally relates to A, then they will appear in that order, A then B. But if they don't, they can, they can swap places as well. Another way that causal ordering really does is source ordering just follows right out of it, right? Source ordering means is that causally these things are related because they come from the same source. So something like the single writer principle falls right into here. You don't have to do anything more if that's how you sort of set your causal relationships up. So the reason why I mention this is just to think, because these things do have sort of an impact on how you would look at relationships within message passing systems. What's the relationship of ordering between these things? It's very seldom that a single message is totally without any relationship. A lot of times a message is dependent on some other piece of data, especially in microservices types of arrangements. Sometimes the design of a protocol or something else lets ordering just fall totally out of it and you don't even have to think about it. And I'll give you the classic example. Application layer framing was an idea that started in 1990 by Clark and Tenenhouse in a SIGCOMM paper. And the idea was if you design a protocol close to the actual thing that you're trying to do with it, you can present a protocol that actually is simpler, more efficient, faster, has all the different buzzwords you want. So I'll give you an example that they used for application level framing. So you have a file you want to transfer. It's a certain length. You're going to cut it up into chunks of a certain size, and perhaps the last chunk is smaller, because you got a little bit left over. But the advantage here is that all you need to know is not the offset of that piece of data, but just to number it, just like you would an array. And if you're thinking about C, this would be an array of whatever you want, because they're all consistent. So if you receive message number 4, you know that you missed everything up, previous to it, if that's the first thing you receive. So if you have a source, he just basically does the simplest thing ever. He just cuts these things up into simple sequences, sends them out. A receiver receives a subset of those. He receives, in this case, 0, 1, 3, 4, 5, 6, 7. So he misses, obviously, 2 and 8. Well, at the end of that, the receiver can say, hey, I missed 2 and 8, and just receive those. There's lots of different aspects to this which are really kind of fun. The first thing is, when I get one of these messages, I know exactly where it goes. So if I were to be putting this into a file, I know exactly the offset in the file that I want to go to, and I just write it into there. How do I calculate it? I take the size of the messages and multiply it by the actual sequence number. That's it. That's dead reckoning. That's dead reckoning of the actual data in an ordered way. Really, really simple, right? Something that Martin and I have worked on called Aaron, a protocol that is used for reliable multicast and reliable unicast, takes this a little bit different. It has an offset, so you can tell when a message comes in by dead reckoning where it actually leads in the stream. In fact, where it leads in the stream over all of time, which is kind of neat. So taking this kind of concept, ordering just falls out. It's ordered, but it's also dead reckoned, so you know exactly what to do with it. If you build a system with it, you can now just write into offsets. Much simpler. So that's kind of, thinking about it a little bit, but a lot of times ordering simply isn't enough. Messages can be reordered, they can be duplicated, and they can be lost, just like we mentioned. And, how do you deal with this? Sometimes, ordering's not enough. You need a little bit more because there may be state attached to it. Or maybe there's not state, but there is some transition that has to happen, some action, some side effect. Well, State machines actually rock. Okay, so I'm an old hardware engineer. I started out as a hardware engineer in VLSI design, and so I'm very used to state machines, and I really like them because I'm weird. And so they actually have a lot of really cool properties. So I don't care how you implement state machines in software. Transition tables, Java enums, JavaScript prototypes, and these are all things that I've done at some point or another. And table with lambdas. Well, okay, not the last one. But you can do a lot of different things with them, and you can implement them a lot of different ways. One of the things that I worked on early in my career was taking a protocol that I designed and then having to beat on it for a couple years, formally proving that the protocol had certain properties. To do this was pulling your hair out a little bit, but it was also really instructive. It taught me a couple things about how to specify complex types of systems. Here's an example of one particular use of a state machine within some Java code. This has one property that I think is key to making state machines readable and deducible. The first is you have the three elements of the current event that is happening, the current state, and the next state for transition, all within one area that you can see. My advice for if you're using state machines is that be explicit, don't hide them behind abstractions, and make them observable, like Martin pointed out. Making them observable means that you can query at any time what this current state is and just get back, here's your current state. And you can, from that, see the list of things that go into it, and all you need is the event stream and the current state, and you can go back, and you can debug them quite easily. One typical thing that I see people do is they'll hide the state machine behind some sort of abstraction. And I really do mean don't hide them behind abstractions. Because once you lose the fact that you can look at the event and you can tell what state you're currently in and where you're going, you would not believe the amount of errors that can creep in just because you lose that visibility. So don't care how you implement it. There's lots of different ways. Implementing it somewhere where you have the ability to see all three of these at once is really pretty important. Also want to state that state machines are actually worth your time to look into. In fact, I want to give you a sort of an idea of how even a bad state machine can give you some really interesting insights. This is the TCP state machine. I told you I was a protocol geek, so we're going to go over this. There will be a quiz later. So there's three different properties within the state machine that have nothing to do with exchanging data. In fact, the state machine has nothing to do with exchanging data. What it all has to do with is I'm in a certain state, what do I do, what do I send, and what should I ignore, in essence. The first thing is, how many of you have heard of TCP reset? Okay. So the way TCP reset works is a beautiful little piece of design that basically says it's really, really difficult to recover from arbitrary errors, so we're not going to. We're going to fail fast. In fact, a TCP session that gets something that doesn't match this sends a reset and goes all the way back into that top state closed. That's all it does. There's no trying to recover. There's no additional things that are tried. It simply fails fast, sends a reset, goes into closed. In fact, every single connection starts in closed. If you get a message while you're in closed, you send a reset and stay in closed. Which means that this is a really simple thing, right? It's not on this transition. There's nothing on that chart that talks about it. It's just if you receive a reset, doesn't matter what state you're in, you go to closed. If you get something that doesn't make sense from this, you go to closed. This is a really important property for software that has to work. Software that has to work because of people dying if it doesn't, like within NASA, within flight software, things like that. There is always an obsession with what happens if something unexpected that we didn't anticipate in the design happens. How can we go into a good known state? In TCP, that's closed. It's kind of interesting. So there are many different problems with this state machine, and I'll just kind of point to the bottom. But there's also lots of things we can realize about how simple certain things can be. Let me give you an example. Anybody ever heard about what simultaneous open means in TCP? Besides it being right up there on the state diagram. You probably would never do this, but imagine if you had two sockets and they connected to one another. Don't really have applications to do that, right? Usually one's a server waiting for connections, the other one is, going to connect. But what happens from a network perspective if you were to see this? Because all it is a TCP message with a certain set of ports and a bit set. How does this get handled? Well, it's actually right here. That's it. There's no special states. There's nothing else that is done. It's simply a transition into the in the state diagram. That's it. Nothing else. No frosting on top. Nothing. It's simply a single transition. Now, how did this evolve? You can sort of imagine, Vern Paxson and others that were sort of, talking around how TCP should work and how they should be able to, what things they should handle. And someone's saying, what happens if both these ends try to connect to one another? What do we do? And somebody looking at the table and going, oh, we just actually do that. We just draw a line, transition into that, and have them both go through the left side. That's actually probably pretty close. I'm not old enough to know if that was actually the case, but it probably was pretty close that was what happened. The design kind of falls out. So sometimes with a state diagram or a state machine, you can look at and see interesting behaviors that are actually inherently there and figure out how to support new activities from just adding transitions without actually adding states, things like that. Notice if you have simultaneous open, someone had to say, oh crap, we also could have simultaneous close, so there's something at the bottom that handles that as well. The other thing is, and this goes along with how to handle unexpected cases, is the whole reason why the bottom looks so messed up. The bottom is there to take care of all the reasons why someone would want to close a connection and there being what's called 2 times the maximum segment lifetime on the network where a message could be duplicated and come back. So lots of what is down there is trying to prevent basically a stray message that could be going around the internet for, at that time, 256 seconds and pop up and mess up a state machine. So most of that's down there was put in specifically to eliminate duplication and to eliminate that that a message could be out there for literally 256 seconds, which, was kind of unrealistic, but we're going to be a little bit careful. So there's lots of different transitions here that allow those different things. This state table or this state diagram would look really, really different if you actually looked at it and said, you know what, we don't really care about one side, disconnecting from the other, and we also, independently from the other. And we also didn't want to support, basically, a server closing versus a client closing and have certain guarantees associated with it. You could actually get rid of most of what's there if you could do that. So there's a lot of different things that you can learn from this state machine. Not in the neighborhood of, how well to design it, because it's not well designed. There's also things in here that are a little bit, skeptical. But the state machine doesn't have to actually be about how the majority of your processing works. It can be, this is how we're going to actually handle all the error cases within an application. How many of you have actually looked at kernel code? Okay. How many go-tos have you seen? A lot. Okay. That pattern of actually doing something, then going to a different part of the function and having different fall throughs for just things that you don't even know can happen. That pattern is actually it's common in Linux, it's common in FreeBSD and all the other BSD variants. It's very resilient. That pattern of, I'm not exactly sure how I'm going to get here, but if I do, I want to do something that, takes care of it. And the safest thing to do. So state machines and things like them are actually worth your time. If you're actually doing systems that have this asynchronous binary boundary between different components in it, and you're going to be doing non-trivial kinds of things, which we all are, then actually looking at some state machines, looking at how things work when they're in there, is actually worth your time, I think. Ordering as well. State machines also have another property. They're very well researched in how to actually test them. In fact, there's two different areas for this. The first thing is, does my code implement it correctly? That's more along the lines of, sort of the branch testing and everything else. The second part is the design safe, correct, and everything associated with that. VLSI testing techniques have just banged the heck out of number 2 in all kinds of different ways, and number 1. So these are things which there's well-known, very established, very repeatable ways to make sure that state machines do what they want to do. The design around them also has a lot of work. Model checking. I spent a good bit of my early career working and doing research for NASA on how to actually do formal verification and validation of software that would be used in shuttle, station, Cassini space probe, and several other things. And I've used model checkers to check behavior in the past. And the best one that I've used in the past is Spin. It's been around for quite some time. It was the 2002 ACM System Software Award. It is basically, I want to explain how, what my system looks like. It's going to then do state exploration out of all the different combinations, and it will tell me if there are invariants that are, that don't work, and where they don't work, and how I got into them. Spin is a fantastic tool in that you can keep a certain amount of that in your head. Once you get a few states and several transitions, it's really difficult. Something that is more, that I think actually Leslie will talk about tomorrow is TLA plus. Now this is something of the same type, very close, has a model checker called TLC within it, but it's a much broader, so specifying things is a little bit easier and a little bit different. So, these things are pretty useful for looking and seeing if your system actually can present you with all the different things it needs to, even if stuff goes sideways. But let's get back, to sort of see here at the end here. If we take systems and we think about message-driven kinds of properties, and we'll even knock it back a little bit and say, asynchronous binary boundaries between components, using that to constrain the designs a little bit, and giving, and hopefully facilitating elastic, responsive, and resilient types of traits with these systems. If we kind of break it down, the thing that is common between all the traits, I'll postulate, is if we think about things as an idempotent unit of work. And from a networking perspective, we would think about this as an ADU, or an application data unit. In other words, what a message would be. What we want there is we want something that has little to no ordering requirement. In other words, it's idempotent, right? We want it to be, stand on its own, and also not have a state requirement, or little to none of that. And that being little to none, meaning if the less we can get away with, the more resilient the system's going to be, the more elastic it's going to be, and definitely the more responsive it's going to be. We actually have really good practices for this in REST. REST has a stateless bit part of it, right? It talks about it being stateless and you sending the context and things like that. That actually is a really good practice, right? Because it eliminates that state. It talks about getting little to no state. That's one way of doing it, right? So if we look at that, what we have with responsive systems then is we want no or less waiting and no or less contention. Our systems become much more responsive when we have little to no waiting and little to no contention. Systems become resilient when we have also little to no waiting and little to no state. There's a whole bunch of other properties, but if we sort of look at them from this perspective, we get that these things will be more resilient and more responsive. With elastic, we want systems that have no contention and no shared state. Once you introduce even a little bit, we actually have the problem that Amdahl will hunt us down like Boba Fett going across the universe so that we can encase ourselves in being encased in carbonate and freeze. So this is what we actually have. If we want to build systems that are responsive and scalable and fast, we have to think about these things. So that's it. Finished slightly early, so we have a little bit of time for questions. Yeah.
The application level framing stuff you talked about, you gave one example.
Yeah.
Was the research they were doing leading towards a conclusion that the different message streams in an application, you have different types of application level framing?
Yes.
So you gave one example there, okay, but there are other things where that you don't need that directly ordering, for example, like what we're doing, right?
Right. Yeah, that's absolutely it. It's the paper tried to address the fact that a lot of times we try to make protocols which are everything to everyone, which means that they're nothing to no one, right? So, you know, what it tried to do was to say it actually is a network version of mechanical sympathy. By understanding the problem at a deep enough level and designing something which is closer to what you want, as opposed to solving a more general problem, sometimes, not always, you end up with something which is really a good match and simple and direct. So it's just like everything, there's no absolutes. Just like I don't think that message-driven is the only way to construct these applications, but I think for what we know right now, it's one of the better ways to sort of start. So application level framing is, it doesn't apply always because sometimes you can't know exactly what the application wants to do. So trying to frame it as something the application wants to do is incredibly difficult. And sometimes it may be the wrong direction, but sometimes it also is the right one too. Yeah.
There's a common theme of statelessness and going through the whole session this afternoon. And the world is, inherently state.
Yeah.
State in the world. How does state fit well into a message passing model when you're trying to make idempotent small message providers and all this stuff? Where do you put state?
That's a really good question. In a lot of systems, instead of referring to some mutable state, like an account record, right? Instead of referring to the record and having the current status of the record, it's a lot of times having the starting status and then all the changes. That's one way of actually reducing state, because now, instead of you having to know everything about that object, you just say, add $5 as a payment, right? So those types of things are really simplistic ways that actually reduce state. So the ideas of append-only structures and a lot of the things like that are actual ways to reduce state, because what they do is they make it much more explicit, or they make state reconstructible. So from a protocol perspective, a lot of times what you end up doing is plumbing. And what I mean by that is, well, okay, you're shipping things around, so yeah, it's kind of like plumbing. But what I actually mean by plumbing is, it's always, I have in the packet, an ID, and I need to look up what state is associated with that and how it might mutate. Trying to actually reduce the amount of mutation on that state is what I've spent a long time doing. I always struggle I don't want to mutate it. I want to just look it up. If it's there, I want to just do what it tells me to do, like the state. That's why one of the reasons why state machines are real useful for me is they're really compact representations that have very explicit transitions. So I only need to know what the current state is. I don't need to know the rest of the state that's associated with it. Mm-hmm. Anything else? All right.
Thank you, Todd. Folks,